concepts. We'll go through them once more. As designers or as engineers, a lot of time we work with storage and tables and databases. What I'm going to do today is introduce you or give a whirlwind overview of what kind of different storage and database options we have. And to do that, first, I'll go through a brief history in terms of how things evolved over the last 40, 50 years of computing, followed by some of the storage options and database options we have available from GCP. So the first is history. Now, let's start with storage. And if you remember, the first computers or the first things which came out, people started programming. The storage or the hard disk at that point, or a floppy disk or magnetic disk or tape or whatever kind of storage was there, was physically connected to the computer, physically connected to the CPU. Some of that still happens today for your desktops and servers where they're actually connected to the CPU. The operating system or the application directly works on a file system, which directly works with the storage controller, all in a single box. And to scale up an application, you scaled up that box. Or if scaling up was not possible, you connected some more of them and did parallel processing and load balancing and all of those things. But soon, as application sizes grew larger and the kind of data which we wanted to store became even more, that kind of a direct attached storage mechanism was becoming inefficient and very, very expensive. Two different technologies sort of took up at that point in time, parallelly, and they still exist to some degree today. One is SAN, or Storage Area Network. The other is NAS, or Network Attached Storage. The key difference is where does a network decouple your compute and storage. Primarily, both decouple your compute or the CPU and the storage through a network layer. Now, first, let's look at the Storage Area Network. What it simply did was it took out all the physical storage-related activities out of the box which was running the application into a separate storage controllers. And your file system on the boxes or on the servers were talking to the storage controllers to store blocks. So your application would give, or the file system would give blocks of data like a 16K block or a 64K block or 4K block to the storage controllers, and they would actually ship that block and store it to the right striped hard disk. The challenge in a SAN or a storage area network was still that the file system was local to the application server, and all the locking and things related to that was done by the file system on that server. Take an example of a network-attached storage. In network-attached storage, the entire file system is remote. So your compute or your application is running on a server, and the storage is completely remote to that particular server with a network layer in between. The network was attaching the storage to the compute in the sense that application doesn't know what's the exact block size or the physical format of that hard disk or of the storage system. It simply worked on the file system operators, and the network-attached storage sort of gave all the file operations to the application. Examples of both of them. So for SAN, the biggest example or the biggest use case for SAN kind of a storage network was your database systems. Database systems had to do a lot of computing before they actually shipped that block out to storage. And that's where SAN was predominantly used for database systems. Your NAS, or network-attached storage, is predominantly used for sharing files or sharing systems, or file-like systems across applications. But in recent past, there has been a true explosion of data, and a data which is what we call immutable, which means the data doesn't change, it's just that more and more data keeps getting added. And for that kind of a problem, a new class of storage evolved, which is called object storage, or also called blob storage. And the name of this particular session is blobs to tables. Blobs stands nothing but binary large object. What it means is applications or requirements came up where you wanted to store and serve large binary data files. Think of images, think of videos, think of logs, where the things are not going to change. It's just that they're going to be consumed, so they're going to be get and put onto the storage. So the entire API system or the POSIX API system of file handling was just too much. And object storage does away with all of that with very few simple operations like get and put. and abstracts away the actual storage so that you can have as much storage as you want, wherever you want it, with a very simplified API. Now, on the database side, the story is slightly different and more interesting. So for the last 40, 50 years, there has only been two eras. One era which started after the internet became big, and the era before that. So it all started first with transactional systems or transactional databases, which were storing all your, let's say, orders, customer data, things like that in what we call a normalized format. When you're running applications like e-commerce or classifieds or any other thing, you're writing to a transactional database, doing transactions, doing very rich row locking, column locking, things like that. Now, if you wanted to run some heavy queries or build some reports on top of that operational transactional database, that would actually really slow it down. So a new class of databases evolved, which is the data warehouse kind of databases. What you did was you ran some jobs or cron jobs or ETLs, basically extract, transform, and load jobs, which pulled that data from your transactional tables or transactional databases and shipped it off to these specialty database systems called data warehouses. Now, the key thing about data warehouses is the data is modeled based on what kind of questions you want to answer. So the kind of questions or the kind of reports or kind of analysis you want to do has to be pre-programmed into the data warehouses so that you could build models. Think of star schema, think of snowflakes, put into a data warehouse. And this is what was state of art for the 30, 40 years till the internet era. Of course, there were innovations where servers were scaled up or the systems were scaled up to handle more and more loads. But essentially, a transactional database, which is housing all your transactions, orders, customer data, for ETL to a data warehouse, which was running all your reports and queries and things like that, was what was there for 30 years. Then, when internet really became big, a lot of data started getting generated. Data which was not just huge in volume, but also different in data types. Pre-internet era, the most common data types was CSV or some other very specific proprietary data types. After the internet era, there are so many now. You have JSON, you have XML, you have n number of different data types. So internet not just brought in explosion of data or ballooning of data, but it also brought in ballooning of data types. The other thing was organizations became more data focused, and they wanted to log as much data as possible from different sources. The reason for that was, of course, storage became cheap. So you had logs data, which was putting all your logs. You had clickstream data from your websites, which was used to analyze how users behave on your website. You have analytics data, a lot of different kinds of data, which was getting generated. Now, putting all of that data into a database system is really, really inefficient, and not just inefficient, very expensive. You can't just put logs data into a table. It will just explode within a few days. So what started happening is the cheapest form of storage at that point in time was log storage, and application developers started dumping all of that logs data and stream data into a log storage, which is more like a file system. The second challenge was, hey, now I have all of this data, but what to do with that data? How do I analyze? How do I pull out insights from that data? And that's when Hadoop-like systems started coming up. Hadoop said, hey, you have all of this unstructured or structured data lying around in your file system-like place. Hadoop can help you analyze that data using Hadoop jobs. Now, you have Hadoop jobs which run all of that data into insights, and then based on those insights, you can design new models which can be put back into your data warehouse. So you have all of these logs and stream data. You run Hadoop jobs, pull out insights, and once you know what kind of analysis you want to do, you create jobs which will transfer all of those data points into a model, into your data warehouse, which can then help you run regular reports on top of that data. But all of this was happening on the analytics side. On the database side, few other interesting things were happening. There was a demand for very wide column databases. Think of thousands of columns. Also, there was demand for databases which could handle documents. Now, transactional databases are good when you have a strong relationship, like a foreign key relationship, between different tables. But not all kinds of data is suitable for transactional or normalized data systems. Let's say you want to store information about the customer. In a transactional database, you will split that information into 10 different tables, create a star schema, join, and then create a view of that customer. In real-world systems, that is very, very complex. Not just complex, it's time-consuming. You want things in milliseconds. Executing joins on milliseconds is nearly impossible. So another kind of data system evolved, which is NoSQL kind of data systems, which help you store document data, or they're called document databases. It stored hierarchical data, assume XML or JSON, which can then be persisted into the tables and queried. The other problem which both of these solved was as you scaled up, problems, the three things which cannot typically happen together is your access, your fault tolerance, and your availability. Now, to do that, NoSQL made some, I would say, NoSQL made some assumptions that, okay, hey, I can give you high availability and high throughput, but at the cost of, let's say, at the cost of consistency. So instead of giving you very strong consistency, NoSQL kind of databases made the trade-off of giving you eventual consistency. Similarly, your very wide column databases are very frequently a key value pair where you want to do a large number of data. Let's say your sensor data is flowing in, or you have time series data. Let's say you're a game developer. You want to store different snapshots of a user journey. So a key value pair through a very wide column tables becomes very easy to store in a wide column database. But soon after these things happened, there was still a demand for transactional databases which could really scale well and give you high or strong consistency, availability, and reliability. And that's where a new class of database systems called scalable RDBMS is developed. Now, Google has, or GCP has products in all of these areas. So for example, for transactional databases, you have Cloud SQL, which supports MySQL, PostgreSQL, and Microsoft SQL, or SQL Server. For analytical databases or data warehouses, we have BigQuery, which we just had a session for, which allows you to store not just gigabytes, petabytes, and terabytes and petabytes of data and run queries at scale. You have managed Hadoop clusters through Cloud Dataproc, and a lot of log storage in form of cloud storage. Cloud Bigtable for your NoSQL, Cloud Firestore for your hierarchical data, and Spanner for your transactional, globally scalable, strongly consistent database. Now, so these are all our products, right from in-memory storage, like a cloud memory store, which is nothing but a managed Redis servers, all the way to file systems, which is Cloud Filestore, block storage, cloud storage, which is object store, BigQuery, which is analytical databases and data warehouses, and all your transactional databases. Now, let's look at storage in a bit more detail. So, cloud storage, it is our object storage solution. It is globally scaled system which allows you storage of immutable objects. And when I say immutable object, it doesn't mean that you cannot change objects on cloud storage. It just means that when you upload the same file name, for example, it creates a different version of that file. Now, what cloud storage offers you is huge amount of storage in gigabytes, petabytes storage in 3 different tiers, depending on what's your use case. So it has a standard tier, a nearline tier, and a cold line tier. The typical use cases for cloud storage is storing your binary data like video, images, typically used for media and entertainment, or to keep your long-term records, or to do a disaster recovery kind of a thing. So let's say you are running an application in Singapore, you have cloud storage in Singapore, and then you can have another cloud storage location somewhere else, which is keeping a replica of all your data. It gives you a very high degree of reliability. Also, cloud storage can act like a data lake for you, because Hadoop can pull data from cloud storage. Your logs can be directly sent to cloud storage. Let's say you're running a VM or you're running a compute engine instance. You can ship your logs directly to cloud storage, run CloudProc or Cloud Dataproc or Hadoop clusters, pulling data directly from cloud storage into your analysis or importing directly into BigQuery. So cloud storage acts like a baseline for all your analytical and storage needs, wherever it's large amounts of data, which is not going to change. The second is persistent disk. This is more like your storage area network. This is key piece of storage which attaches to your VM. So let's say you're running compute engine or you're running VM instances. Every VM needs a storage. And persistent disk is that storage for you. It allows you to keep a file system and attach it to your VMs as and when required. It allows scale up and scale down. It has two major tiers, standard and high performance. High performance is actually backed by SSDs or solid state devices. It gives you a very high IOPS. At the same time, it is resizable, which means you can start off with a small size and then keep scaling up your storage depending on your needs. You can share disks between different VMs if you need to in read-only mode and things like that. They act just like your hard disks or virtual hard disks. They have some cool features like auto snapshotting for ensuring that things don't go bad, or if they do go bad, you can recover from them. Then you have Cloud Filestore. Cloud Filestore is more like your NAS or network attached storage. So this is designed for applications which expect a file system like APIs underneath it. It supports full POSIX API for file systems. And as with most of our storage systems, it comes in two different tiers, standard and high performance, which is regular hard disk and solid state devices. Now, the key uses for file stores are, let's say, your publishing or media applications, things which expect a file underneath them. Now, let's say you are moving to cloud. You have on-premise data, you have on-premise systems which generate a lot of data. You want to move all of that data into cloud, and let's say you have terabytes or petabytes of data. Transferring that amount of data over network is going to take hours or days sometimes. And for that, you have a transfer appliance. It's a 1U rackable device which you can put into your data center or put into your data place. Transfer all of your data locally to this particular appliance, which stores 1 petabyte of storage. Ship it to Google, and Google will load all of that data into cloud storage for you. So transfer appliance is for you to help ship lots of data from your on-premise systems or an on-premise data center to cloud. Now, let's look at a demo of how quick and fast cloud storage is. And I'll need just a minute to boot up my Chromebook. Awesome, and we're back online. Cool, so as I said, cloud storage has 3 tiers, which is standard, nearline, and cold line, and they're for different needs. So standard tier is typically for your active usage where files are going to be, or the objects which you're storing on them are going to be used across the globe. Nearline and cold line is typically for disaster recovery, where the cost of storage is really, really low. It's just that the cost to access is slightly more. You can have lifecycle systems or lifecycle events set up on cloud storage, which can transform your objects from standard to nearline to cold line if you want. What I'm going to do now, or what I'm going to show you now, is how quick and fast cloud storage is for you. What I've done is, let's create a data bucket in US. So creating a data bucket is just like clicking there and let's say sample US data bucket. You give it a name which is globally unique. And then you say, where do you want to store? You say US, for example, and then choose the tier. For now, let me actually choose a cold line tier. And I have already created a bucket in US, which is cold line. What I'm going to do now is, because we are in Singapore, I went out taking a snapshot of Esplanade. I'm going to put this onto my blog, and for that, or WordPress, I need to put that image globally. So what I'm going to do now is actually drop that image onto cloud storage. So it gets uploaded, and it's available. Now, I share this file to public. So doing that is just editing permissions, and I can add permissions to make it public. So now it's public. And you can take that particular link, for example, and see how long it takes. Mind you, the storage is actually in US. So what I'm going to do now is I'm going to spin up a machine in, so Southeast 1 is actually Singapore. So I'm just going to SSH into that machine now. And what I'm going to do is copy that file here. Less than a second, about a second, including the file storage. So that's how fast it is to pull that data from US to Singapore, even on a cold line system. Let's go back to the slides. Awesome. So now we see that how fast and easy it is to store things on cloud storage. Some benefits of storing on cloud storage is Google automatically terminates requests to your cloud storage objects which are public to the nearest point of presence. So Google has a lot of points of presence across the world. Let's say your user is sitting somewhere trying to reach out to this particular object which is stored onto your cloud storage. The request doesn't need to travel entirely on the internet from the user's location to the cloud storage location. What happens is Google routes that request to the nearest point of presence, and from there on, it travels onto very high-speed Google internal system or Google internal network, which serves the data very, very quickly. It also edge caches all of those things very near to the user. Now, let's look at databases. Now, databases are an integral part of any application development. What we provide is a way to complete all of the requirements the business had in an innovative way, in a way which is integrated well with all the other things which you're doing as part of your application development. So, few offerings from GCP on cloud databases is Cloud SQL. Cloud SQL is a managed SQL service which helps you run PostgreSQL or MySQL, and very soon it will allow you to run SQL Server as well. So this helps you scale up, scale down without the hassle of spinning up a VM, imaging it, transferring data, keeping a backup, creating high availability. All of that are just configurations which you can do onto Cloud SQL, and it all is taken care of. So it is a managed database service which helps you run any kind of transactional databases which you want. Those databases can help you then run your applications. The security is key here, so a lot of effort has been put into ensuring that the database systems are not open to public, or you can define how open your database systems are. There's an internal network through which you can obviously connect to the database without exposing the whole server externally or to the world. The other kind of database system which we have is Cloud Memorystore. It is a managed Redis system. It allows you to, or helps you do a lot of in-memory metric calculation, HLL, whatnot. And it's a fully managed system which takes care of very high IOPS. Typically used for creating scorecards or gaming, where you want to keep a lot of metrics in memory and query them very, very fast. Don't want to go the query to actually get into a disk mode. So to show you how easy it is for you to help, or easy it is for you to migrate your SQL from on-premise or wherever you're running your SQL servers. Sorry, when I say SQL servers, I mean any transactional servers to Cloud SQL. I'll show you a demo of how easy it is to spin up a SQL server and then connect your application to it. Awesome. Can we switch to the laptop? Cool. So in GCP console, you have the SQL as a section. And in that SQL, you can go in and say, create instance. When you create instance, it gives you two choices. Which one do you want, like MySQL or Postgres? Let's say I choose Postgres. Now, what I do is I go through a form of filling up what I need or what configuration I need. Let's say I say server 1 or whatever name I want to give. You can provide a password for it, or you can generate a random password if you want, depends completely on you, what you want to do. You can choose the region where you want to spin up those servers. You can have a server closer to your application, closer to the compute engine instances or VMs where your data or where your application is going to run. And then you can choose which Postgres, which Postgres version you want. There are a few other bells and whistles which make sense to tinker right now. So for example, what you can do is you can choose how many cores or how much memory you want in your Cloud SQL instance. And depending on that, your throughput will vary. And there's a nice looking graph which tells you how it varies. So you can move all the way up to 64 CPUs or simply one CPU depending on your need. So let's say I put 8 CPUs typically. And depending on that, you can see the throughput changing. The memory also keeps changing. You can adjust your memory. Then on the storage front, you can choose high performance SSD storage or regular HDD. SSD is recommended because it gives you very high performance. Typically, your Cloud SQL allows you to scale up or increase the size of storage, but it's advisable to allocate more disk in the beginning because it gives you more IOPS. So instead of resizing the disk every time, you can actually start with a high disk size, anticipated size which you feel your database will need, which will give you a very high IOPS in the beginning so that your database read-write operations are very, very fast. And that's it. You just say create, and it will start creating the instance for you. Now, while that instance is getting created, I wanted to show you how easy it is to run your applications or port your applications from on-premise SQL systems to Cloud SQL. So what I've done is I've created a demo, which is a voting system. So let's say it's a Python program, which is a simple, very, very simple Python program, which gives you a UI to choose two things. So let's say I start with that. And it spins up a small local server, and I can connect to it. And there's a gotcha here, which I want you to see. So when I do this, there's no database. I didn't spin up, or I didn't connect to any database. So what I'm going to do now is, let's say I will spin up a small SQL server on my own system. Let's say it's a Docker. I run a local Postgres in Docker. And it is alive. So let's refresh this page and, oops, let's restart the application. And you have the application running on a local Postgres server. You can put votes and things like that. So this is a simple application, and it works. Now, let me actually turn down the local. Let me turn down the local Docker, which is actually running my database. Stop. So that instant, the local server goes down, and it's still on. OK, it has gone down, and the application has stopped working. Now what I'm going to do for you is actually patch this application to the Cloud SQL server, which I have spinned up in the cloud. And what I'm going to do is there's a very easy-to-use command or application which is available to you called Cloud SQL Proxy. You can run here. You can specify the cloud instance which you want to connect to, provide the port numbers, etc. And what's happening now is it is creating a small proxy locally so that your application can connect as if the server is running locally. But it's actually running from cloud. And you see there are some boards already there which I had put in onto the cloud server. So it's that easy to switch from a local database system to Cloud SQL by either using Cloud Proxy or SSHing into it or any other way. So Cloud SQL works just like your local SQL servers. without the headache of managing any systems. And also, if you're running test environments, it's very easy to spin up different SQL servers for different environments and connect to them depending on your need. Can we switch back to the slides, please? Awesome. So we have spoken about transactional databases, and no transactional database conversation can be complete without talking about Spanner. Spanner is a very unique system which allows you to store large amounts of data, but it is a transactional database, globally consistent, globally scalable, highly available. So this is something which is not easily available with any other provider. It gives you globally consistent or globally strongly consistent queries. So let's say you insert a row or you do a transaction in US, and then you are running a query in Asia. The result you get from Asia is going to be strongly consistent with the result you're going to get in US, irrespective of what that transaction was. Now, this is something which Spanner provides you with. It gives you scale. It can not just scale regionally, which means it not just helps you run scaled or replicated databases in one region like Asia. It helps you run globally consistent transactional databases. The definite trade-off here is the query time. So typically, you expect tens of milliseconds of query time. If you are in a globally consistent, strongly consistent state, the query times are going to increase, but not to seconds. They're going to go to, let's say, 100 seconds, 120 seconds, but it's going to be strongly consistent. So that's the trade-off. And you need to decide, or you need to think about what your application really needs. Does it need really strongly consistent view? Then Spanner is for you. Otherwise, we can definitely look at other NoSQL kind of databases. First one is Cloud Bigtable. Cloud Bigtable is a fully managed. When I say fully managed, in case of Spanner or in case of Cloud SQL, it was managed, but it was not serverless, which means, and same is with Bigtable. It is not serverless. You have to decide how many computing nodes you want, but it can scale to the size or to the level you want it to run. It gives you very high consistency and response times in single-digit milliseconds, typically used for storing time series data. So a lot of ad tech, it is a key value pair kind of a thing. It's a wide column database, typically used by ad tech and fintech. It is used to run real-time analytics. It can connect to BigQuery for your visualizations in real time and stuff like that. Now, let's look at Firestore. All of these were systems where you had to decide how many nodes you want, how many compute do you want. Cloud Firestore is a truly serverless, so you don't need to decide how many nodes globally you want. It automatically scales up and scales down depending on your query needs, depending on your storage. You have to do nothing. It gives you query results in tens of milliseconds. It's nearly strongly consistent across the world. But it is a document storage system. It's not relational system. So it does not have relational entities between or relationships or a foreign key kind of things between them. It's a key value pair or a document store. It does have query semantics, but the query semantics are very, very limited. The key benefits here are very quick query times for an object kind of a thing. Let's say you're looking up a user profile, a user logs in. Instead of joining things across 10 different tables in a normalized structure, you pull that document out of Firestore and serve that to the user. It supports real time, where multiple clients can be connected to the Firestore, and all of the views will automatically get updated in real time. So all of these real-time capabilities are built into Firestore. Typically used by gaming applications or application developers for mobile applications, but also definitely usable for desktop applications or web applications. BigQuery, I think previous session touched a bit upon it. BigQuery is our data warehouse built in cloud, designed for cloud, truly serverless. You don't have to provision anything. You just load data, run queries. It helps you run petabyte-sized queries in seconds time. You have infinite capacity in terms of storage, and it is truly next-gen. It connects to most of the data storage systems we spoke about and can help you federate data for your analytical needs. So BigQuery helps you do analytics, run dashboards, and things like that. So after going through all of these, the key thing is what is the ideal or the right application or the right product for you, it totally depends. Now, an application can use one or more of these solutions or products in itself. So for example, I built an application which uses Firestore to store user profiles, puts all of the clickstream and log data into BigQuery, runs BigQuery jobs to run real-time analytics and show a dashboard of users. I can dump my data into cloud storage for media files if I'm running a blog system. So the kind of system which you want to use totally depends on your application, and you can mix and match all of them for your needs. Thank you.